Welcome to an exploration of one of nature's most fascinating phenomena, when liquids enclose air instead of the other way around. Imagine a bubble, but not as you know it. Instead of air surrounded by a thin liquid film, picture a droplet of liquid surrounding a pocket of air. This is the inverted droplet. Let's first understand what makes inverted droplets so special by comparing them to normal systems. In a normal droplet, liquid forms the core and is surrounded by gas or air. In a normal bubble, gas is inside, with a very thin liquid shell around it. But in an inverted droplet, we have gas inside with a much thicker, more substantial liquid shell. Here's a visual comparison. Notice how the inverted droplet has a much thicker liquid shell compared to a normal bubble. To understand inverted droplets, we need to understand surface tension, the key force at play. Let's ask ourselves, what exactly is surface tension? Surface tension is the energy cost required to create new surface area between two phases, like liquid and air. Mathematically, surface tension gamma equals the change in energy per unit change in area. The units are joules per square meter, or equivalently, newtons per meter. For a water-air interface at room temperature, gamma is about 0.072 newtons per meter. At the liquid surface, molecules experience an imbalance of forces. Molecules in the bulk are pulled equally in all directions, but surface molecules feel a net inward pull. The Young-Laplace equation governs the pressure difference across curved interfaces. The pressure difference equals surface tension times the sum of the reciprocals of the two principal radii of curvature. For a perfect sphere, both principal radii are the same, equal to r. This simplifies to delta P equals 2 gamma over r for a spherical interface. What does this equation tell us about the physical behavior? It tells us that smaller droplets have much higher internal pressure. Pressure is inversely proportional to radius. Here's a graph showing how pressure difference increases dramatically as radius decreases. This inverse relationship is crucial. Let's calculate the pressure inside a normal water droplet to build intuition. Consider a water droplet with radius 1 millimeter, or 10 to the minus 3 meters. Using water's surface tension of 0.072 newtons per meter. The pressure difference equals 2 times 0.072 divided by 10 to the minus 3. This gives us 144 pascals, which is about 0.14% of atmospheric pressure. This is quite small compared to atmospheric pressure of about 101,000 pascals. However, if we shrink the droplet to just 1 micrometer radius, the pressure jumps to 144,000 pascals, larger than atmospheric pressure. Now let's explore how inverted droplets actually form in nature and in the lab. One method is vigorous mixing or shaking of liquid and gas together, trapping air pockets. Another method uses surfactants during emulsification to stabilize the gas core inside liquid shells. Modern microfluidic devices can precisely create inverted droplets by controlling flow rates. In a vigorously mixed system, we get a complex mixture of inverted droplets of various sizes distributed throughout the liquid phase. A critical question is, how stable are these inverted droplets? Let's ask, why don't these inverted droplets immediately collapse and release their trapped air? The answer is that surfactants at the interface provide kinetic stability, creating an energy barrier. The lifetime scales with viscosity eta times radius r divided by surface tension gamma. Higher viscosity means the liquid drains more slowly, extending the droplet's lifetime. Interestingly, smaller droplets can be more stable because their higher internal pressure resists collapse. Over time, the surfactant layer shown in yellow stabilizes the droplet, though the air core gradually shrinks as gas diffuses out. Inverted droplets exhibit interesting buoyancy behavior due to their composite structure. The buoyancy force equals the liquid density times total volume times gravity. The weight includes both the liquid shell and the much lighter air core. So do these inverted droplets rise or sink in the surrounding liquid? It depends on the shell thickness. Thin shells make them float, thick shells make them sink. The net upward force approximately equals air density times core volume times g, since air is much lighter than liquid. Here we see inverted droplets rising through the liquid medium due to their buoyancy, similar to normal bubbles but with different dynamics. An important phenomenon affecting inverted droplets is Ostwald ripening. What exactly is Ostwald ripening, and why does it matter? Ostwald ripening is when larger droplets grow larger by consuming smaller ones through diffusion. Remember, smaller droplets have higher internal pressure than larger ones. Gas molecules diffuse from high-pressure regions to low-pressure regions. The rate of radius change cubed is proportional to surface tension times diffusion coefficient. Gas molecules, shown as yellow arrows, diffuse from the small high-pressure droplet to the large low-pressure one, causing the small to shrink and large to grow. Inverted droplets have fascinating applications in food science and technology. Whipped cream is essentially inverted droplets, air bubbles trapped in a stabilized fat matrix. Bread dough contains carbon dioxide pockets trapped in the elastic gluten network during rising. Ice cream is even more complex, with air cells, ice crystals, and fat globules all interacting. These food structures rely on stabilizing air pockets within continuous phases, creating the textures we love. Inverted droplets are related to, but distinct from double emulsions. Double emulsions have structures like water and oil in water, or oil and water and oil. Inverted droplets are simpler, just air and liquid, but with a substantial liquid shell. We define shell thickness ratio as outer radius minus inner radius, divided by inner radius. A thin shell with ratio less than 0.1 behaves like a normal bubble. A thick shell with ratio greater than 1 behaves more like a solid droplet with a void. Here's a visual comparison of different shell thickness ratios. Notice how the behavior changes dramatically with thickness. Let's analyze the energy involved in creating and maintaining inverted droplets. Surface energy equals surface tension times total surface area. For an inverted droplet, area includes both outer and inner surfaces, 4 pi r outer squared plus 4 pi r inner squared. Which costs more energy, a normal droplet or an inverted droplet of the same size? The inverted droplet costs more energy because it has an additional inner surface that a normal droplet lacks. Total energy for inverted droplet includes both interfaces. Normal droplet has only one interface, so lower energy cost. This energy graph shows inverted droplets require more energy to form than normal droplets of comparable size. Inverted droplets behave in interesting ways when subjected to flow. When fluid flows past them, inverted droplets deform from spherical shapes. The capillary number equals viscosity times velocity divided by surface tension. At low capillary numbers, surface tension dominates and droplets remain spherical. At high capillary numbers, viscous forces dominate and droplets elongate, potentially breaking apart. Here we see progressive deformation as flow strength increases. Yellow arrows show flow direction. Inverted droplets respond uniquely to acoustic waves due to their compressible air cores. The air core can oscillate and resonate when subjected to sound waves. The resonant frequency equals 1 over 2 pi r times the square root of 3 gamma p0 over rho. Smaller inverted droplets oscillate at higher frequencies than larger ones. This property makes inverted droplets useful as ultrasound contrast agents in medical imaging. The droplet pulsates radially in response to acoustic pressure waves, emitting scattered ultrasound. When inverted droplets collide, they can merge in complex ways. Do inverted droplets merge easily when they touch, or do they bounce off? It depends on the collision energy and surfactant layer strength. The Weber number equals density times velocity squared times radius, divided by surface tension. At low Weber numbers, droplets bounce elastically without merging. At high Weber numbers, the thin film between droplets ruptures and they coalesce. Two inverted droplets approach and merge, forming a single larger droplet with a combined air core. Temperature significantly affects inverted droplet behavior. Surface tension decreases linearly with temperature. Gamma of T equals gamma 0 minus K times T minus T0. Higher temperature means lower surface tension, making droplets less stable. Gas solubility in the liquid also changes with temperature, affecting core composition. The ideal gas law governs the air core. Pressure times volume equals nRT. Heating causes the air core to expand, while cooling causes it to contract. Notice how the air core expands as temperature increases from cold to hot conditions. Let's explore some cutting-edge applications of inverted droplet technology. In medicine, inverted droplets can encapsulate therapeutic gases or carry drugs in their shells. In material science, they serve as templates for creating controlled porosity in ceramics and polymers. In acoustics, arrays of inverted droplets can create metamaterials with unusual sound propagation properties. They also function as microreactors, providing isolated environments for chemical reactions. These applications leverage the unique properties of inverted droplets to create innovative solutions. In conclusion, inverted droplets are fascinating entities with unique properties and applications. Inverted droplets consist of air cores surrounded by substantial liquid shells, which provide stability and control over the air-liquid interface. Inverted droplets can be created through various methods, including vigorous mixing, emulsification, and microfluidics. The stability of inverted droplets depends on the presence of surfactants, shell thickness, and surface chemistry, which influence their behavior and interactions. Inverted droplets have the potential to revolutionize various fields, from medicine to material science, by providing a unique platform for encapsulation, templating, and reaction.